Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about oscillations and simple harmonic motion. Now, our objectives include analyzing simple harmonic motion in which the displacement is expressed in the form a sine omega t or a cos omega t, recognizing simple harmonic motion when expressed in differential equation form, calculating the kinetic and potential energies of an oscillating system, analyzing problems involving horizontal and vertical masses attached to springs, finding the period of oscillations for systems involving combinations of springs, and deriving the expression for the period of a pendulum, both an ideal pendulum and now for the first time a physical or real pendulum. So, simple harmonic motion is motion in which the restoring force is directly proportional to the displacement of the object. The more you displace it, the more restoring force there is trying to bring it back to its initial position. The reason this is so important is, in general, nature's response to a disturbance is some sort of simple harmonic motion. You can see it all over the place. Bend a blade of grass, watch it come back up, simple harmonic motion. Or a snowy tree that's weighed down, a limb with lots of snow. As the snow falls off and you see the branch go back and forth. All of these responses have restoring forces proportional to the displacement of the object, or at least that's a good starting model, and is simple harmonic motion. You can even see it in the atoms of an object. When they're compressed or stretched, they will vibrate back in simple harmonic motion. So let's take a look at simple harmonic motion and start off with an analogy to circular motion. Let's assume that we have some mass moving in a circle of radius a at some angular velocity omega, and at a given point in time, its position vector is given by a cos theta, a sine theta, where a is the radius or the magnitude, cosine theta, that's the angular displacement. So that's our x-coordinate, and there's our y-coordinate. And we're going to compare this to a system of a spring attached to a wall with the mass on the end. And we're going to pull the mass, displacement a, from its equilibrium or happy position and let it go back and forth. What's really amazing about this analogy is if you were to pull this to A and let it go, you can compare its x position to what you would get as this object goes around the circle, its x position. As the circle goes around at any given point in time when it's over here, the mass is going to have that same x component all the way around. So you get this nice analogy between what we're already familiar with, circular motion, and this mass moving on a spring in simple harmonic motion. So let's start out by taking a look at the angular velocity there. We know is the time rate of change of the angular displacement. But if I rewrite that a little bit, if I separate our variables, we could write that omega dt equals d theta. And if I integrate both sides from some t equals 0 to some final time t, integral from theta equals 0 to some final theta, then that implies, well, angular velocity is constant in uniform circular motion, so the left-hand side becomes omega t, and the right-hand side just becomes theta. So theta is given by omega t. That'll come in useful later. And if we go down and we want to analyze our spring block system, we could look at it from terms of Newton's law, from the perspective of Newton's law. F equals ma, and that force is a restoring force minus kx. But we also know that acceleration is the second derivative of x with respect to t squared. So this means that m d squared x dt squared equals minus kx. Or I could write this in the more common differential equation form, d squared x over dt squared plus k over m times x must equal 0. So we have a second-order differential equation, where the second derivative of a function plus a constant times that function gives you 0. Only one way I can think of to solve these sorts of things, and that's with a sine or a cosine, the only functions where their second derivative added to themselves can give you 0. So the general form of our solution, x is a function of time, is given by a, our amplitude cosine, omega t, where we're going to find omega is the square root of k over m. Or if we look here in our equation, that piece right there, that is omega squared. Let's take it a bit further as we look at